In this video, I'll be teaching you guys about resistors in series and a kind of shortcut cheat method in order to solve for the voltage at any resistor. And this is called voltage division. And I'll cover the formula for that. It's a very simple formula for that as well. I'll also teach you how to add equivalent resistances in resistors in a series. So let's go ahead and start off with a circuit diagram of what looks like a resistor in series. So what is a resistor in series? Well, it's basically when the resistors are end to end. So when you have a constant flow, one direction for the current to flow through, then you have a resistor in series. And you can honestly tell that these are already resistant in series, just one singular path that you can take. And in resistors in series, the currents are all the same. All the same. So everywhere throughout this circuit, the currents are all the same. The current at this voltage source is I of S. The current at this resistor, it's called I1. Let's call this I2. Let's call this I3. And let's call this I4. They are all equal to each other. And you can actually use KCL to show this. So let's go ahead and mark the nodes. There's a node here. There's a node here. Remember, nodes are just connection points between elements. There's a node here. There's a node here. There's a node here, and there's a node here. Nodes don't always have to be in the corner, by the way. Just if you were confused about all these corner dots, they can be in between the elements as well. Let's go ahead and use KCL. Well, there's only one current going into this node and only one current going out. So I of S equal to I of 1 at this node. And in this node, I of 1 is going in, and I of 2 is going out. It's only one going in and one going out, therefore they equal each other, and so on. Oh, shoot. I put a node here. This is wrong. This is wrong. There's a node along this entire back section of your circuit. And once you really calculate a single current, you have the currents for the entire circuit. And that makes it very, very easy to solve for all the voltages using just simple Ohm's law at all of these resistors. As long as you have the resistance, of course. But a little thing that you can actually do with the resistors in series is add up all the resistors. So when electricity is flowing through a circuit, there is always going to be some output at the end of it, or maybe there's going to be some, I don't know, some predictable result, right? Well, what you can actually do is set this circuit equal to another circuit. And this circuit has only one resistor. So let's say if this resistance was 1 ohm, this was, oh, that's a very bad ohm sign. This is 2, this is 3 ohms, this is 4 ohms. What you can actually do is add up all the resistors in just resistors in series. So keep in mind, you can only add the resistance of all the resistors if it's in series. So if we add up all these resistances, 1, 2, 3, 4, you get 10 ohms, right? Well, 10 ohms is what we call the equivalent resistance. So if you were to just cut off this part, the left and right portions of these green lines, and say how the electricity flows through on each side, then basically what happens is the circuit only sees all the resistances as just simple 10 ohms combined together. So however much the voltage drops throughout each of these resistances is the same as however much just a single 10 ohm resistor drops the voltage. So what you could do is just have a resistor that is the equivalent resistor of what's actually happening throughout the entire circuit. Because as the current flows through the circuit, the voltage is dropping, right? Resistors drop voltage, calculated by Ohm's law. And as the voltage drops throughout each resistor, and keeps flowing through and keeps flowing through and keeps flowing through and comes out on this side, then it's just going to be the same as if you had a current going through a 10 ohm resistor. So the voltage drop will be the same throughout all of this. So basically to the right side of these green lines, the circuit sees the exact same things in this diagram and in this diagram. And also, when you just have a single resistor, it's significantly easier to calculate anything, right? One resistor, you don't have to worry about a bunch of KVLs, right? If all of these voltages are unknown, and you wanted to use KVL to solve for any of the voltages from this voltage source, it'd be completely impossible. So what you can do instead is just add up all the resistors and then use KVL on a single resistor. And I'll be showing you guys how to use that in this video as well. But let's go ahead and talk about voltage division. So what you see here is voltage division, and it's a very simple formula. So let's go ahead and draw a circuit diagram to show you what I mean by why it's simple. So let's say you have resistors in series, two resistors in series. R of n and V of n are corresponding components of a resistor. So R of n is the resistance of a resistor, and V of n is the voltage drop of that resistor. So if you want to find the the voltage of a resistor using voltage division, you have to use the resistance of that resistor. You cannot use the resistance of some other resistor. And Req, we've already established, Req is simply when you add all the resistances in series. Now, keep in mind, you can only use voltage division when they are in series. Do not use this when they are in parallel or in any other format. Alright, and what is V of S? Well, V of S is basically just the voltage going into the circuit. So in this case, we have a voltage source, and hopefully they give you the voltage that the voltage source is providing of the circuit. This could also be V of in some textbooks, and this could also be V of out in some textbooks. But essentially what it's saying is V of out is the amount of voltage that's actually getting out of the system due to the resistor, right? The resistor drops the voltage from the direction of the current. And V of S is simply the voltage going into the circuit. And V of S in this case is provided by a voltage source. So we're going to head and do some problems and show you how to actually apply your knowledge for voltage division and resistors in series. For this problem, I'm going to be using two methods to solve this. So whenever you see a circuit, there's multiple methods to solve it. You could use, but in real life, you're just going to use a multimeter to see what the voltage actually is. But you can use a circuit diagram to actually predict the results. But let's go ahead and rewrite the circuit diagram so that there's only a resistor equivalent. So our voltage source stays the same. It's 20 volts, but we want a single resistor. And we notice that all these resistors are in series, correct? Therefore, there can be a resistance equivalent, and that resistance equivalent is calculated by adding all the resistances in the series circuit. So 5 plus 3 plus 2, that's simply 10 ohms. And VEQ we'll write here. All right, now we have a current equivalent, and I of S is still the same. Okay, well, the reason why we did that is because if we use KVL here in the counterclockwise direction, you're going to notice that you have all these voltages, V3, V2, and V1 are voltage rises, and the voltage source is a voltage drop. Well, we only have the voltage as a voltage source. We have 3 unknown voltages, so we cannot use KVL in this case. So what we can do is, of course, add all the resistors, and then now we can use KVL. Doesn't matter which direction, I'll go counterclockwise. So if we go counterclockwise, this VEQ is a voltage rise, and this is a voltage drop. So V of S is a voltage drop. Well, we don't have VEQ, but we do have VS. It's 20 volts provided by this voltage source. Therefore, VEQ is equal to 20 volts. Well, if it is equal to 20 volts, we can just use Ohm's law. So 20 volts over 10 ohms is equal to the current equivalent. And that is simply 2 amps. So 2 amps is the current going through this circuit. Well, we know that this is a resistor in series. Therefore, once we solve for the current, we solve for all the currents. So every single one of these currents are 2 amps. 2 amps, 2 amps, and 2 amps. So now that we have all the amps, we can use Ohm's law in every single one of these resistors. So for V1, we use Ohm's law. 2 amps times 5 ohms is equal to 10 volt drops. V2 and V3 are calculated like so. 2 amps. V2 has a resistance of 3 ohms, and V3 has a resistance of 2 ohms. So we have 4 volts, and we have 6 volts here. Well, if you actually add up all these voltages, 10, 6, and 4, you realize that it equals the voltage drop given by the resistance equivalent here. But we can also use voltage division. So voltage division is Vn is equal to V of S over with R of N over Req. Let's write that a little better. Let's go ahead and write down Vn. So Vn is our unknown, but we want to solve for V of 1 in this case. So V of S is 20 volts. The R of N is the resistance at V of 1. So R of N is R of 1, which is 5 ohms, over the resistance equivalent, which is we calculated to be 10 ohms, right over here. So we have 20 times 1/2, which is just equal to 10 volts. And we calculated that V of 1 using Ohm's law is also 10 volts. And if you use voltage division for the rest of this entire circuit, you'll realize that it all equals the same answers you got from using Ohm's law. So voltage division and using a resistance equivalent and then finding all the currents and then using Ohm's law, they all work, okay? Voltage division and Ohm's law, they should give the same answer. If they don't, though, it's a good sanity check for you. Of course, if you do voltage division and you have extra time on an exam. But if you do it, wow, you get a different answer. Either your math was wrong for voltage division, or you just calculated the circuit wrong, which is at least good to know so you have time to fix it. But let's go ahead and move on to the next question. Let's go ahead and solve this circuit. So of course we're going to start off with using resistance equivalent. So let's find Req. Req is 20 plus 10 plus 15 plus 5. That's simply, and let's write that down. Write that down up here. Req is equal to 50 ohms. So if we draw our new circuit diagram, we just simply have one resistor that is 50 ohms. Plus, and we have a voltage drop equivalent, and we have a current equivalent as well. We have I of S, and our voltage source produces 100 volts. All right, now that we have this, we can use KVL. KVL has all the voltage rises as VEQ, and voltage drops as 100 volts for a voltage source. Therefore, VEQ is equal to 100 volts. All right, well, we have 100 volts here. We can use Ohm's law. So 100 volts divided by 50 ohms is equal to the current equivalent, which is 2 amps. And as we've stated, the current across an entire series circuit is always the same. Therefore, all the currents in this circuit are 2 amps as well. 2 amps here, 2 amps here, and 2 amps here. Well, we can just calculate all these voltages individually using Ohm's law. So V of 1, V of 2, V of 3, and V of 4. We have 2 amps on everything. 2 amps, 2 amps, 2 amps, 2 amps, times. So V of 1's resistance is 20 ohms. V of 2's resistance is 10 ohms. V of 3's is 5 ohms. And V of 4's is 15 ohms. All right, now that we have this, 2 times 20 is 40 volts. 2 times 10 is 20 volts. 2 times 5 is 10 volts. And 2 times 15 is 30 volts. So if we add all these, 40 plus 20 plus 10 plus 30, it'll equal to 100 volts. And 100 volts is our calculated resistance, our calculated voltage drop equivalent. So this is a good check, right? Okay, well, we can also use voltage division. Let's go ahead and use voltage division. V of 1 is equal to V of S, or the voltage going into the circuit, times the resistor that we're trying to calculate the voltage at, over the resistance equivalent, which we calculated was 50 ohms. So what we have here is 100 times 2 over 5. And that is equal to 20 volts. Sorry, not 20, 40. What am I saying? So 40 volts. And 40 volts is equal to the calculated V1 that we used Ohm's law for. So you can go ahead and use voltage division as well for all the rest of the ones if you want to check it, but it's good practice, especially if you have time on your exam.